Hello everyone, today we are going to discuss the laboratory frame of reference and the center of mass frame of reference. This topic is actually taken from the collision chapter, that's from the mechanics paper. So first let's look at the outline of this presentation, what this presentation is actually going to contain. This is a brief introduction to the presentation. So this presentation is basically going to contain the first we are going to discuss the types of collision in this presentation, because we are going to need this while discussing the other parts of the presentation. Then we're going to actually move to the important part, that's the laboratory frame of reference, and then we're going to discuss the center of mass frame of reference, and then we're going to discuss the most main highlight of this presentation, that's we're going to discuss animation by which we are going to learn how to actually convert the parameters that are actually given in the laboratory frame and the parameters that are actually given in the center of mass frame of reference. We are going to convert these parameters from laboratory frame to the center of mass frame. So this is what we are actually going to learn in this example, because what is actually happening when we are actually learning two frames of reference, so these two frames of reference, then if we actually don't discuss how to actually convert the parameters from one frame of reference to the other frame of reference, then the whole point of this discussion actually remains half. So for that we are going to actually take this example to make a more clear understanding of this topic. So let's move on to the first types of collision. What are the actually the different types of collision? So this is, let's recall, everybody knows this topic. So for elastic collision, what is going to happen, to be very precise, here the momentum is going to be conserved and the kinetic energy is also going to be conserved. But in an inelastic collision, what is actually going to happen is that the momentum is actually going to be conserved, but the kinetic energy is not going to be conserved. So these are two examples that I have put, these are two animations that I have put of one of elastic collision, the other is of inelastic collision. So in the first example, if you can see that these are air molecules actually colliding with each other, and when you actually consider the collision between the air molecules are, though they are not perfectly elastic collisions, because whatever may be the collision, it may when the collision happens in the microscopic level or macroscopic level, there will always be some amount of energy which will actually be lost during the whole collision process. So though these air molecules does not collide with perfectly elastic fashion, but then also we can actually consider them as a elastic collision. And this is actually an example of inelastic collision. You can see that this all these different balls are actually colliding with themselves, colliding with each other in a random manner. So what is going to happen in this process is there's lots of energy and lots of heat, or different forms of energy is going to dissipate during this collision. So this is a perfect example of inelastic collision. Here they are moving so much randomly, they are losing lots of energy during the collision. That's the kinetic energy. They are losing the kinetic energy. This kinetic energy, all these particles actually have, is actually lost during this collision. So this type of collisions are example of inelastic collision. There are some more examples of inelastic collision, like crashing of two cars, two marbles actually hitting with each other. So these are all these are actually examples of inelastic collision. In the real world also, most probably whatever collisions we actually see is all inelastic. There are very, to be precise, very less number of cases where we will get perfectly elastic collisions. So let's actually go to the next frame, that's the laboratory frame of reference. So this is the start of the main part of this presentation. So if we actually go with the main definition of the laboratory frame of reference, what the definition says, according to the definition, the reference frame which is at rest with respect to the colliding particles is called a laboratory frame or lab frame of reference. So you should note this, that this laboratory frame is sometimes called a lab frame in real world use cases. So the main highlight of this definition is that this frame, laboratory frame, should be at rest with respect to the colliding particles. Now what is this actually statement? Let's understand this with the help of a diagram, and we are also going to include an animation at the end to understand this more better. So let's move on to the diagram to understand this better. So now if we see, this is actually a lady which is actually standing at the origin of this frame, and let us consider this as the laboratory frame of reference. Now this is the x-axis, this is the y-axis, and this is the origin of the laboratory frame of reference, and this lady is actually standing at this origin. Now what, let us consider during this presentation that whatever will be the observations of this lady, because she is standing at this origin of the laboratory frame. So whatever will be her observation, we are going to consider as her observations as the observations of the laboratory frame of reference. Now for this lady, what is actually the mass m1 is at a position vector r1, and the mass m2 is at a position vector r2. Now this mass m1 is moving with initial velocity u1, and mass m2 is actually at rest, and this is the point of the center of mass of these two particles. Now according to the properties of the laboratory frame of reference, the coordinates are actually fixed. Now suppose if these two particles actually come and collide with each other, or move away from each other, then what this lady is going to observe this whole event actually standing at a particular position. So this is actually quite a handy frame of reference. That is why this frame is actually used quite extensively in real world applications to actually make real world measurements. So yes, this frame actually needs only one property that is to be fulfilled, that its coordinate points are actually fixed. So for this lady to be a valid as observer for the laboratory frame of reference, this lady should be actually standing in a particular position, and that's enough for him, for us to actually consider this lady as the observer of the laboratory frame of reference, provided this lady does not move during the whole event. She should be stationary during the whole event. Once the whole event actually is over and all the measurements are actually taken, then this lady can actually move. But this lady should not move during the whole collision process or during the whole event. So that is the only one condition of laboratory frame of reference. So the coordinates are fixed. So this is actually the only one and only condition. So used for making actual experimental measurements. So this, as I actually discussed, this laboratory frame is actually quite handy because the coordinates are only need to be fixed. So this is the only property that a frame should actually fulfill to be called as a laboratory frame of reference. So this is quite handy in the real world. Actually, whenever we are actually standing in a particular position and actually observing an event, then we are actually the observer. We can actually call ourselves as the observer of a laboratory frame. Uh, so this perfectly explains why it is used for actually making day-to-day life experimental measurements. And for the next parts of this presentation, we are actually going to make a consideration, because that m2 is at rest. Okay, so we are, throughout this presentation we are going to consider the collision and in which one particle will be at rest, because it's going to make the explanation more simpler throughout this presentation. So let's now move on to the center of mass frame of reference. Hope you understand what is called a laboratory frame of reference. So if we go to the center of mass frame of reference, the definition, what actually the definition says is that a reference frame with its origin at the center of mass of the system is called the center of mass reference frame, or C frame of reference. So what is the main important thing about this definition is that about the center of mass frame is that the origin of the center of mass of the system is called the center of mass frame of reference. So a reference frame which is such that it's actually present present at the center of mass will be called as a center of mass frame of reference. Now let's understand this definition of center of mass with the help of a uh, diagram. So actually, as I actually discussed, that this lady is actually the observer of a laboratory frame of reference, and this is the x-axis and this is the y-axis. These are the laboratory frame axes. Now according to this lady, m1 is the position vector of m1 is r1, the position vector of the center of mass is r, and the position vector of mass m2 is r2. Now all these parameters that are actually marked with black color, or the parameters or these factors that are marked with black color actually signify that uh, these are the actually parameters of the laboratory frame of reference observer, and all the different factors and parameters that are marked with red color will actually signify the parameters of the center of mass frame of reference. Now what is center of, now let's move the whole thing to the center of mass frame of reference. Now to be valid as a center of mass frame of reference, the observer should be actually standing at the center of mass frame, or should be at the center, observer should be at the position of the center of mass. So whenever the this condition is fulfilled, like the observer is actually standing in the center of mass, then whatever will be his observations, or whatever will be his point of view of the whole collision process is going to be taken as the observation for the center of mass frame of reference. Now for the for this observer to be actually valid as an observer of the center of mass, he should actually fulfill few of the conditions. So these are four or five conditions that he should actually fulfill to be actually call himself as the observer of the center of mass frame of reference. So the first condition is the origin should be the center of mass. So for him, the origin should be the center of mass. So he is actually standing at the center of mass. So the first condition is actually fulfilled. The origin should be the center of mass. Now uh, the position vector of the center of mass should be 0 according to this observer. Now actually, as he is standing at the center of mass, so for him obviously the position vector of the center of mass is going to be 0, because as he is standing at the center of mass, he is not moving with time. He is actually standing at the center of mass. So position vector of the center of mass will be 0 for him, and the position vector of mass m1 will be r1 dash, position vector of mass m2 will be r2 dash for this particular person. Now whenever uh, he is standing at the center of mass, what he will observe that the velocity of the center of mass is also 0. Now to understand that why the velocity of the center of mass according to this observer will be 0, suppose if one person is actually sitting in a car and actually moving with some velocity, if the suppose car is moving with some uniform velocity, then if somebody asks the person who is actually sitting in that car that what is the velocity of the car, so obviously that person who is actually sitting inside that car will say that the velocity of the car is 0, because he will not feel his own motion provided the car is moving with uniform velocity. He will only see that all the other objects are passing by him. He will not actually feel his own velocity. In the similar manner, when a person is actually standing at the center of mass, so what is going to happen? So wherever the center of mass actually moves, this person will also move with the center of mass. So that is why this person will actually not feel his own velocity, though he is moving with respect to some other frame of reference. But according to his observation, as it is always mandatory that he remains with the center of mass. So wherever the center of mass will move, he will also follow with the center of mass. So he will actually not feel the velocity of the center of mass. So when he actually don't feel the velocity of the center of mass, so according to him, the velocity of the center of mass will be 0. And when the velocity of the center of mass according to this person will be 0, the momentum of the center of mass according to this person will also be 0. So that is what I have written. The momentum of the center of mass according to this observer of the center of mass observer will be actually 0. And the fifth property is this center of mass frame is also called the zero momentum reference frame. Now why it is called zero momentum reference frame, we are going to understand this with the help of an example. So let's move on to the example. So this is the most eye-catching part of this presentation. That's the we're going to analyze an inelastic collision of two masses m1 and m2 of 2 kg and 5 kg in lab frame and C frame of reference. Sorry, this is not going to be inelastic. This is going to be perfectly inelastic collision. So here the what is actually provided in the question is the velocity of mass m1 is 10 meters per second and mass m2 is at rest in laboratory frame. We are actually given with the parameters of the velocity. We are given with the velocities in laboratory frame of reference. So now what we are actually have to find is that the final velocity of the two bodies after collision. since one body is 5 kg and one body is 2 kg, one of the two bodies is stationary and one of the two bodies are actually moving at 10 meters per second speed velocity. So before collision, this is the case of before collision. So after collision, what will be the final velocity should be that is what we actually need to find. So we are going to find the final velocity of the two bodies after collision. Then number 2 point, what we are going to find is the velocity of the center of mass in left frame of reference. So this is also what we need to find. In the left frame, what will be the velocity of the center of mass? Because as the two bodies actually, when they are actually coming towards each other, the position of the center of mass also change as the two bodies come closer to each other. So that is what we actually need to find the velocity of the center of mass. Then what we are going to do at the third step is we are going to shift the parameters to C frame of reference. We are going to shift all the parameters that we have in the laboratory frame of reference to the center of mass frame of reference. So now let's understand the whole situation with the help of an animation. Let's move on to the animation. So now what is this animation is going to see is that suppose here are actually two particles. So this is one particle, this is another one particle, and this red dot actually is the center of mass. So now when this particle actually comes and collides with this particle, so this is the type of perfectly inelastic collision that's going to happen between these two particles. So this is the scene before collision. So this is after collision, what is going to happen. Now this body is actually moving at 10 meters per second, and this body was actually at rest before collision. So after collision, these two particles will stick together with each other and move as if these two particles are actually a single system after collision. So we actually need to find is the velocity of these two particles after collision. Next, what we are going to find is the velocity of the center of mass after collision or before collision. So as this two particle approaches, the center of mass also moves towards this particle as this particle comes towards this particle. So we are going to find this velocity of the center of mass in laboratory frame of reference, that is this ladies frame of reference. So if we look at the actual parameters here, so what is actually given, this first mass is 2 kg and the second body is of 5 kg, and the first body is moving at 10 meters per second. So it is the case before collision, and initially this mass of 5 kg is actually at rest. So this particle will come with 10 meters per second and collide. So after collision, what is going to happen is these two particles will actually stick together with each other and move with a finite velocity. So these particles are going to move with the same velocity after collision. So this is an example of perfectly inelastic collision. So actually, to find the final velocity after collision, what formula we can employ is that we already know that the initial velocity will be equal to the final velocity, since whether it is an elastic collision or whether it is an inelastic collision, one condition is mandatory, that the momentum will always be conserved in both the cases. So according to the law of conservation of momentum, what formula we can employ here is that the initial momentum of the two bodies before collision will be equal to the final momentum of the two bodies after collision. So what will be the momentum of this body according to this lady's observation, that is the laboratory frames observation, is 2 into 10, that's it, 2 mass into velocity, so 2 kg into 10 meters per second. So this will be the momentum of this particle, and 5 into 0 will be the momentum of the second particle. Since it is at rest, this thing will obviously be 0. So this whole thing will be the initial momentum of the system, and this will go the final momentum of the system. Since these two particles actually collides with each other, and after collision, what happens is both the particles will have the same velocity. So after collision, what happens is both the particles will have the same velocity. So what we can see is that velocity we can take common, and 2 plus 5 is the mass of this 2 is the mass of this orange ball, and blue is the 5 is the mass of this blue ball. So when we actually calculate the total mass of the system, it's going to be 7 kg. So and this whole system is going to move with this final velocity. So if we calculate all these different things, then what we'll get is the final velocity after collision is 2.86 meters per second. So this was the first condition that we had to actually find. Now what we are going to find is the velocity of the center of mass. That is what we are going to find according to the laboratory frames observer. What will be the velocity of the center of mass? That is what we actually need to find now. So if we see actually this before collision, these two part as these two particle approaches, this center of mass also approaches towards this particle, and after collision what happens is that uh, these two particles these two particles will stick towards each other, and the momentum and the center of mass is also going to be somewhere in between these two particles. And as these two particles move with 2.86 meters per second, as we have just now found out, so this center of mass is also going with velocity 2.86 meters per second after collision. So this is the case of after collision. So after collision, this body moves at 2.86 meters per second. This body moves at 2.86 meters per second. Center of mass will also move at 2.86 meters per second. So that's you can visually actually recognize this. So what we can conclude that the velocity of the center of mass after collision is 2.86 meters per second. Now, for some of you may be confused, what will be the velocity of the center of mass before collision? So for the case of the velocity of the center of mass before collision, we can actually employ another one formula for mechanics. According to this formula, what happens is uh, the the final momentum or the initial momentum is always equal to the mass of the system times the velocity of the center of mass. So this is the formula what we can actually employ. So I will repeat it again. The initial or final momentum of the system is always equal to uh, the mass of the whole system times the velocity of the center of mass. So this is the formula we can use to actually find the velocity of the center of mass before collision. So in this particular case, the velocity of the center of mass before collision will also be 2.86 meters per second. So that I have not mentioned this specifically, but when you actually employ the formula, you can actually find the velocity of the center of mass uh, before collision is 2.86 meters per second. So this may be different in different cases, but in our this specific case, it's actually 2.86 meters per second for both before collision and after collision. So what we actually get, we already found out two parameters, that is 2.86 meters per second and velocity of the center of mass according to this lady's observation, that is the laboratory frames observer, is 2.86 meters per second. Now we actually have the velocity of the mass m1 is 10 meters per second. This mass is stationary. Final velocity of the two particles after collision, all these parameters that we have at this point is for the laboratory frames observer. Now we are going to find the observations that the center of mass frame of reference is going to make. So we are going to shift all these parameters from laboratory frame of reference to the center of mass frame of reference. So for that we are going to look at the next animation. So let's look at the next animation. What we are going to analyze the event in C frame of reference. So now this boy is actually standing with the center of mass, or it's actually standing in the center of mass. Now what happens during the collision? Let's see the animation. So this is actually what happens during the collision. Now what happens, we actually made one property. There is one property of the center of mass frame of reference, is that wherever the center of mass actually moves, the observer of the center of mass will also have to move with the center of mass. So that's a mandatory condition. So now as this ball actually comes towards each other, these two balls actually come towards each other. So the center of mass will also come towards this ball. So this boy will also have to run with the center of mass to actually keep up with the center of mass for him to be a valid as a center of mass frame of reference observer. So this boy will run with the center of mass. Wherever the center of mass will go, this boy will also follow with the center of mass. So this is the whole collision process that's going to look in the center of mass frame of reference. So now let's look at the parameters. So if now according to the laboratory frame observer, what is the velocity of this particle is 10 meters per second. Now according to the, just now we have found that the velocity of the center of mass according to the laboratory frame observer is 2.86 meters per second. So we have marked this in black color. Remember that, as I previously said, the parameters that are actually marked in black are the parameters for the laboratory frame of reference, and the parameters that are marked in red are actually for the parameters of the center of mass frame of reference. Now, since he is actually the center of mass, and the center of mass, those at the center of mass may move with respect to another observer, that's the laboratory frames observer, he will actually not feel the velocity of the center of mass. He will feel as if he is running in a single place, like people are running in gym in a single place, no? So in that similar fashion, he will feel like that he is running in a single place, the center of mass is present at a single place. What he will actually see is the relative velocity of the two particles. He will not see his own running. Though he is running, he will feel that he is running in a single place. He will not move forward also, he will not move backward also. So according to this observer, according to a lazy observer, this boy may run and move forward, but according to him, he will be running at a single place, like running in a treadmill. So he will observe the relative velocity of this particle and relative velocity of this particle. Now according to laboratory frame, this particle was having a velocity of 10 meters per second. He is moving at 2.8 meters per second according to the laboratory frame observer. So what is this person actually going to observe the velocity of this particle? So he is moving, this is moving with 2.8 10 meters per second, he is moving with 2.8 meters per second. So the velocity of the this particle according to this observer would be 10 meters per second minus 2.8 meters per second is equal to 7.14 meters per second. So this observer is going to observe the velocity of this particle as 7.14 meters per second. Now what will this particle appear to him? What will be the velocity of this particle that will appear to this particular person which is standing, is who is actually following with the center of mass frame of reference? So what we got, so before initially before the collision process, so this particle was at rest. So this center of mass was slowly shifting and moving towards this particle. So as you see in the animation, this center of mass actually moves towards this particle. So though this particle is stationary for the observer in laboratory frame of reference, what this person will actually observe is that this particle is actually coming towards him. He will not observe his own running. He will feel that he is running in a single place, as was already said. He will only see that this particle actually comes towards him with 2.86 meters per second, as he is running forward with 2.86 meters per second. So this ball, according to this observer, will be actually coming towards him with 2.86 meters per second. So that is what this boy is actually going to conclude. So according to this boy, the velocity of this particle will be 2.86 meters per second. But according to the laboratory frame observer, this was at rest. So this is coming with 7.14 meters per second. This ball is coming towards him with minus 2.86 meters per second. So the directions are opposite actually. Now the main condition is the main case is what will be the final velocity of the two particles after collision according to the laboratory frame observer. So that is what is most important about this presentation. So now if we see actually before collision, this thing I have explained to you already. So after collision, what is going to happen as the center of as this two body according to a laboratory frame observer is moving with 2.86 meters per second. This body is also moving with 2.86 meters per second. The center of mass is also moving with 2.86 meters per second. The boy is also running with 2.86 meters per second. So this will be a whole system after collision, or this will be a whole system of same velocity, that is 2.86 meters per second. All these four objects will actually move with 2.86 meters per second. So what will this man actually see? The velocity of the two particles after collision is zero, because these two balls are also moving at 2.86 meters per second. The man is also moving at 2.86 meters per second. So according to this man, these two balls will be actually stationary. But according to the laboratory observer, these two balls are actually moving at 2.86 meters per second. But this man will conclude that these two balls are actually at rest after collision for him, for this man, because he is moving at 2.86 meters per second with the same velocity as the two balls are actually moving. So what we can conclude that the final velocity of the two particles after collision will be 0 meters per second according to this observer. It's already written in red. So all the red parameters are actually the parameters of the laboratory, center of mass frame of reference. So now I have made a statement that the center of mass frame is called the zero momentum reference frame. Now why it is called actually zero momentum reference frame? Now when actually a observer in the center of mass actually tries to find out the momentum of the whole system, whether it is before collision or after collision. Let's verify this. Okay, why it is called zero momentum reference. So if he tries to find out the momentum of the system before collision or after collision, what will he actually see the momentum of this particle? According to this observer, the momentum of this particle will be 2 into 7.14 meters per second. The momentum of this particle, according to this observer, will be 5 into minus 2.hs meters per second. So when this whole thing, when you actually calculate this whole thing, then what we get is the total momentum. That is a total momentum according to the center of mass frame of reference will be actually zero. So that is why it is called the zero momentum reference frame. So this is one of the mandatory conditions of the center of mass frame of reference. So whatever type of collision may be, whenever a observer is standing on the center of mass, you will always observe, or you will always calculate the momentum of the whole system as zero, whether it is before collision or after collision. So this is a mandatory condition to be recognized as a laboratory frame of reference. So zero momentum reference, and that is why laboratory frame of center of mass frame of reference is called a zero momentum reference frame. So now we have actually discussed the laboratory frame of reference and the center of mass frame of reference. So let's what's going to be the takeaway from this presentation. So if we see the main highlights of the center of mass frame of reference, the origin in center of mass, the origin in center of mass. Okay, so here the origin of the center of mass frame is actually the origin of the the center of mass. So wherever the whatever the center of mass is, the origin of the center of mass frame will also be in that position. So if the center of mass shift to some other place, the origin of the center of mass frame will also move with the center of mass. So that is what I have mentioned here, the origin in center of mass, origin in center of mass, in center of mass frame of reference. So the next point is the frame may move with center of mass. So this is what I actually explained. The wherever the center of mass actually moves, this origin of the center of mass frame, that is the observer of the center of mass frame, will also move with the center of mass. But this was not actually the case in the case of laboratory frame observer. However, maybe the motion of the two particles, wherever may be the center of mass, this lady is only going to stand in a particular position and actually observe the whole position. The lady is actually independent. The position of this lady, or the position of the lady's left frame of reference, is actually independent of the motion of the two particles. But it was not the case in the case of C frame of reference, as whenever these two particles actually move towards each other, the center of mass is also going to move. So this center of mass frame is also going to move with the center of mass. So to conclude that this the the position of the center of mass frame is actually dependent on the velocity, the position of the two particles that are actually colliding. So uh, in left frame, what does it conclude that the coordinate is fixed? Now I explained you already what is it. The motion of the particle does not affect the frame. As I already explained, the two particles, whether they are colliding or they are moving away from each other, they will always the left frame observer is always a stationary person, will be actually observing it from a stationary point. She will be actually standing in a particular point during the whole event. But in the center of mass frame of phase, that was not the case. As the center of mass actually shift with the position of the two particles, the center of mass frame is also going to move with the center of mass. So that's what you can actually take away from today's presentation. So I would like to conclude my presentation with this. So I would like to thank you all for giving your time to actually understand this topic with me, and thank you all of you for a valuable time.